Hello everyone, welcome back. We will continue with our amino acids and now we will analyze the imidazole group of histidine. Histidine, now let's remember the structure of histidine. Histidine has a cyclic structure. The R group of it has a cyclic structure and it is basic. Now we will see why it's basic. It has, first of all, an amine group, and it has, of course, its acidic group, and then it has one carbon over here, and then it has a cyclic pentane. All right, and now I will show you a little trick in order to draw the pentane. Now, first of all, we will draw the pentane like this. We will get two branches over here, and then we will start to close it, and we make the roof of it, and then we are done. Now, I want to emphasize now the first way upwards. We will have firstly one double bond, and the other part we will have a nitrogen and nitrogen. All right, now don't confuse yourself with a hydrogen. I will then show you how to do that, and then we will have another double bond and another nitrogen. All right, so first of all, in order for the nitrogens to be able to resonate, we should put the nitrogen over here, and then we will see why. And now we need to place another double bond, and this double bond should be well, actually it doesn't matter, but let me put the double bond here, and let me put the positive charge here. Why? Because double bond and positive charge need to be near each other, so that this double bond can go towards the nitrogen in order for it to complement the valence electrons of the nitrogen. So now that we know this is positively charged, we are going to add, as we know, nitrogen has 5 valence electrons, and for it to be positively charged, it needs to have 4 electrons, so that 4 electrons means -4, and here we had -5, so that it means we have 4 bonds instead of 5 bonds. So we have now, however, as we noticed, we have 1, 2, 3, we need the 4th one over here, and let's place a hydrogen. And then similarly, we will have, as we said, 5 electrons over the nitrogen. We will have 1, 2. The third one, I will draw a hydrogen, and then we will add the 2 valence electrons as we did before. All right, and this is how we are going to write the imidazole group of histidine. So what did we do? We had, just to revise it real quick, we had this structure over here, and then 2 branches, one closing up, and then 1 double bond, another hydrogen over here, and then we had another double bond bringing together a positively charged, and then this is our last nitrogen. And then what do we have to do next? We are said that the imidazole group of histidine is a heterocyclic aromatic amide. Only one of the imidazole nitrogen is basic, the other is lone pair, is part of the aromatic system. So I will show you now why this is aromatic. I will show you why this is basic. So histidine, actually, we are of course, we know that the molecule itself cannot be positively charged. It actually is 1, 2, 3, 4. It actually has. It doesn't have a positive charge over here, and it doesn't even have a hydrogen. It's just like this. The molecule itself is just like this. However, when we add one more hydrogen, it is added to this part, forming this structure. And therefore, as we can see, this is stabilized. What does that mean? It means that when we add an hydrogen and it becomes stabilized, it means that it is a strong base. And how can we show the resonance structure of this? This lone pair goes to here, and then this one goes to here, and we have here a resonance structure. Sorry. It means we have 2 electrons over here, and then a hydrogen. And then this nitrogen is now positively charged. And then we have, as before, we have the rest of our group. And this is our result. We finally, oh, I forgot here, these electrons come to here to form a bond, and then this bond comes over the other nitrogen, and then this is our final result. All right, and then if we do the workup step, which means that we are going to add water, what does that mean? It means that it will take a hydrogen to form a hydronium ion. However, which hydrogen will it take? It of course will take this hydrogen in order to neutralize this charge over here. So let me show you real quick the result. And here we have that. Here we have this, and then we have the following. And this is our result. Plus we have, of course, hydronium ion. And the pKa of this is 6.10. Why so? The reason why is because even though we can gain an electron through this part of this, we have a very important remark that we should see over here. Remark: one of the imidazole nitrogens is basic. Now let me write this here is imidazole. Imidazole means we have a cyclic thing, because like immediate means that it's fast, so it's faster than a 6 carbon ring, as it's 6 is greater than 5. This is just a way to memorize which one was imidazole. And then now let's go back to our remark, and our remark says that only one of the imidazole nitrogens is basic. We have 2 nitrogens, all right? Only one is basic, the other is lone pair, is part of the aromatic system. What does this mean? This means that actually our compound, which had a structure like this, the R part had a structure like this. We have an N here, we have a double bond here, and then our NH is actually belonging here. And now we have actually one of the nitrogens is added to the aromatic ring, because 1, 2, 3, 4, 5 here now we will see which one is part of the aromatic ring. When we add this one here, this one here, this one here, as we can see, these 3 actually made a complete tour, which means that they are resonating. And let me see if the other one was a candidate of being part of the aromatic system. Let me add it here, let me add it here. Now, since here, if this wasn't added to the aromatic ring, there wouldn't be any electrons which were going to be transferred to the other side. That's why we can say that this one is actually part of the aromatic system and not this one. All right, So an easy way to memorize this, to see how that works, it's that we need to have a specific distance between the two electron pairs. So here, as we can see, we have the electron pair here, here, and here, which the three of them form a equidistant sort of triangle, whereas if we were drawing like this, we had one of them here, one of them here, one of them here, and these two regions overlapping were a hint for us to understand that these two are actually not the part of the aromatic system. And now let's continue. The imidazole group of histidine is a heterocyclic aromatic amine. Only one of the imidazole nitrogens is basic, the other's lone pair is part of the aromatic system. And this is the things that we already discussed. And then now let's see the titration curve when glycine is titrated with sodium hydroxide. Okay, so what was glycine? Now, let me remind you real quick what was glycine. We had an amine group, and then we had an acid group, and then we had we had two hydrogens which were both responsible for this carbon being not stereogenic center. When we add sodium over it, what will happen? This is now glycine. Now, first of all, we need to see from the table if what is the pKa of glycine. Now, let me search for its value. And now that I found glycine, I can see that its pKa has its pKa has no value. That means that it's not acidic, not basic property, and then it means that we will have, first of all, both of them, as it's very, very acidic, both of their hydrogens will be taken by the matrix, and then we will have at this point over here we will have a let me write first of all the axis, the OH concentration, let's say, and then we have the pH, and here we had really acidic conditions, so both of them groups will be protonated, and then we have hydrogen and hydrogen over here, and then when we go through the pH of the carboxylic acid, we will see that we will have both of the amino acids equal amount. Let me show you here. Here here we will have both of the amino acids. This is the pKa1 equals 2.35, which is the pKa of carboxylic acid, and then in here we will have both of the amino acids, first of them being the protonated one, and the second one, the carboxylic acid group losing its hydrogen, and this is the molecules that we will observe when we have the pKa1 value. Now let's observe what happens when we have pi value. What was pi? Pi was the the average sum of the pKa1, pKa2 over 2. This is the point where we have the Zwitter ion. Let me write it over here, Zwitter ion. This means that the molecule itself has a net charge of 0. So we will have both, not both. We will just have the amine group. The amine group, we will write it positively, and acidic group, it will be negatively charged. So hence, let me write it over here. We have positive charge, we have negative charge, we have the 2 hydrogens, and as we can see, the total, we have a 1 positive, 1 negative, and the total makes 0. And then let's go on. We have the pKa2, which is the pKa of the amine group, and this group and this pKa tells that we have both molecules, which one of them is we already had deprotonated the acids. Let me write them real quick. And then we already had 2 hydrogens, and then one of the amine groups will be NH3 plus, and one of the amine group will be NH2, because as the matrix is so basic, it will take 1 hydrogen from half of the molecules, and then the final here, this place, it will have both deprotonated groups. Let me write real quick the molecule over here, and then we have the acidic group deprotonated, NH2, the amine group deprotonated, and we have the 2 hydrogens, and this is the end of our titration. And now let's observe what will be the titration curve when alanine is titrated with sodium hydroxide. What was alanine? So first of all, we need to see real quick what the structure of alanine, and alanine had just 1 methyl group as an R group, and it doesn't have any acidic or basic properties. That is why we actually have a really similar graph. However, we should know that if pKa values for an amino acid are known, the fraction of each protonation state can be calculated using the Henderson-Hasselbalch equation. This permits the titration curve to be calculated, or pKa to be determined from a titration curve. Now let me write it real quick. If we know the remark, let me say remark, this is really important, as if pKa values of an amino acid are known, the fractions of each protonation state can be calculated. Values for an amino acid are known, the fractions of each protonated state can be calculated using Henderson-Hasselbalch equation. So what does that mean? As we know, amino acid has a acidic group, an amine group, and then an H and then an R. If we know the pKa values of this one, pKa1, pKa2, if we know the pKa values, then we also know the fractions of how many are found in which pH value. So what that means is we know that they are found half-half in these points over here, half of that molecule, half of this molecule. However, what if we are here? Then we need to use the Henderson-Hasselbalch equation, which is really easy. pH equals pKa plus logarithm of A minus over HA concentrations. This permits a titration curve to be calculated or pKa to be determined from a titration curve. Alright, now let's go on. Titration curves are observed because amino acids are both acidic and basic groups, hence exist as Zwitter ions close to neutral pH. At high pH, both groups are deprotonated, and at low pH, both groups are deprotonated. This is just a part that I read from our notes, and this is the thing that we already talked, so I am confidently skipping this part. And now we have the isoelectric point, the pH at which the majority of amino acid molecules in solution have no net charge. Now let me write this definition real quick. The pi value is the isoelectric point. Let me write it over here because we need to know its what it stands for. Isoelectric point. And then what does that mean? The pH, we have a pH value at which the majority of amino acid molecule, at which the majority of amino acid molecules in solution have no net charge. As we can see here, it says the majority. So it is ideally, it's theoretically, we know that all of the molecules should have zero net charge. However, this is not really possible in real life, and therefore we just say that the majority of amino acids molecules have no net charge. For example, let me give an example for glycine. Let us see that for glycine. So what was the structure of glycine? Let us remember that. A small review on the amino acids. Glycine is a special case. We all need to remember that. It means that it has only hydrogen as an R group. So how can we remember this? It has an acidic group, it has an amine group, and then let me write here, and then we have two hydrogens. So glycine is like glass. And we can remember it like hydrogen is like a really small molecule which passes through all the light, and then also glass we can see through it very well, and therefore we can associate these two like this. And this is obviously not a true way of remembering. It's just a way to make our memory work better and more efficient during any exam or so. And therefore, like as we said, glycine, like glass, which tells us that our R is just made up of one hydrogen. Well, how can we do that? We are going to, the pi of this molecule is going to be 1/2 of pKa carboxylic acid plus pKa of amine. All right, and then making this calculation, we will see that our result is this one. All right, and then this is the end of our discussion of this topic, and then let's continue. So for the 13 amino acids with a neutral side chain, if we had a neutral side chain, let me here write pi calculation. And if we had a strongly or weakly acidic side chain, strongly or weakly acidic. And then we have basic side chain. How do we calculate the PI calculation? So, for the 13 amino acids with neutral side chain, PI is the average of pKa1 and pKa2. This is the average of them. And for the 4 amino acids with either a strongly or weakly acidic side chain, PI is the average of the 2 lowest pKa values, all right? Average of the 2 lowest pKa values. All right, great. And then for the basic ones, similarly, PI is the average of the 2 highest pKa values. 2 highest pKa values. Great. Now let us continue. Now, for example, we will analyze lysine. What was lysine? Let me find its structure real quick. Lysine was basic, and yes, I found lysine. Now I will illustrate why this table is right. Lysine has a such a structure. We have the acidic part over here. We have that amine group over here, and then we have 1, 2, 3, 4 carbons. 1, 2, 3, 4. 4 carbons and an amine group attached over here. And this is lysine. Now, how can we memorize that? Lysine is like lying. As we remember, Pinocchio's nose is getting longer when he lies, and as we can see, we have a long chain which can be associated with lysine, and we have both amine groups. So how can we memorize this one? Now we have a enzyme which when is added to this matrix doesn't know whether to go to this base group or this amine group, which is some sort of tricking the compound, which can be associated with lying too. That is why we can basically remember that lysine had a long chain with an amine group in this form. Now I will show you what is the pKa and then the PI value of this compound. So first of all, let me write the compound again. We had this one, and we 1, 2, 3, 4 carbons, and then another one. First of all, we have a high pH, meaning that and we have a low pH, meaning that we have high concentration of hydrogen, and therefore we have hydrogen both in here, both in here, both in here. Every hydrogen place is protonated easily because the matrix is really acidic. All right, decationic form of lysine. Its name is decationic form of lysine. All right, great. And then we have a pKa of 2.2. This is the pKa of the carboxylic acid group, this part, because it's really strong acid. And then when we start to add a little bit of hydroxide ion concentration over here. When we start to add hydroxide ion, this is the reverse reaction. we will note that the first thing that disappears it will be the hydrogen group of the acid naturally, right? Now let me copy this so that I can easily draw on it. Copy, paste. And here, this is the first thing that disappears, and this is the monocationic form. This is the decationic form. This is the monocationic form. It has a pKa of 9.0. Because now we are stuck with these amines which are basic. All right, and then going a little bit further away, we will note that the first the amine of this part will be deprotonated, and we will have such a compound. All right, and then again we have the same. This is the dipolar ion. Sorry, I'll just... Okay, we have the negative charge, positive charge. It's therefore dipolar ion, and it has a pKa of 10.5. It's a very high pKa, and then we finally will have our last compound, which doesn't have neither of the protons. All right, and then this is our final structure, which is the anionic form. All right, great. And then the pi. In order to calculate the pi, we will just add up the two highest ones, pKa, this one and this one, as the amino acid is in general a basic form, 9.0 times 10, and all right, this is it. And therefore, we basically get the average of the two highest pKa's, and that was our way of finding our way through the pi. And then now let's make another example. Now in this example we have an acid like that, and here this is glutamic acid. Alright, so glutamic acid has two carbons, and as we already said, aspartic acid, as it starts with the first letter of the alphabet, it just needs to have one carbon between its amine group and its R side chain carboxyl acid group. All right, and now this was just a way to memorize what is the structure of glutamic acid and what does the example tells us. What is its form in strongly acidic solution, and in basic solution, what at its isoelectric point, and D asks us the D is the isoelectric point of glutamine. The pi of glutamine, pi is 5.7, is considerably higher than that of glutamic acid, is higher than the pi of glutamic acid. Why? These are our examples. So first of all, the first one is really easy. What will be in strongly acidic solution? All of the groups will be just protonated, and therefore we will just have all of the groups protonated, and this will be our answer. What will be its form in really basic condition? Let me put the solution over here, smaller. And really basic solution, what will it be? All of them will be deprotonated, right? This is our answer. In basic solution, sorry, I copied the wrong molecule. Let me do that real quick. This will be our answer in basic solution. All right, and then at C, it asks its form in isoelectric points. In isoelectric points, two different structures might survive, and those are two Zwitter ions, and one of them might be the one that the Zwitter ion means that we should have one positive and one negative charge. Now here I put the positive charge, here we have the negative charge, here we have the positive charge, here we'll have the negative charge. So both of them are Zwitter ions. However, which one of them will survive? Well, this one will survive. The reason is because of the acid strengthening inductive effect of the alpha aminium group. Alpha aminium group, which one is this one? This one is acid strengthening because means that the acids which are near to this alpha aminium group are more acidic, meaning that it has a greater tendency to lose its proton. And why is that so? It is because it has a resonating structure, and one of them will go there, and therefore making this more negatively charged, and therefore this will go here so that it will be more resonating, more stable. And now we are asked why the pi of glutamine is higher than glutamic acid's pi. It's because now let me show you glutamine. Glutamine is very similar to glutamic acid. However, instead, at the end of the side chain, instead of being a carboxylic acid, we will just have an amine group, and this makes it a glutamine. And this has a greater pi because amine is eventually a base, and therefore its acidic and basic properties will neutralize. Therefore its pi will be greater, closer to neutral values. And the result is written as, since glutamic acid is a dicarboxylic acid, acid must be added to suppress the ionization of the second carboxyl group and thus achieve the isoelectric point. Glutamine with only one carboxyl group is similar to glycine or phenylalanine, as has its isoelectric point at a higher pH. just as we already explained. Now, we are asked the arginine group, and we have already explained it. And now we will continue with our isoelectric point of peptides and proteins in the next lecture. Thank you for attending this lecture. Have a great day.